Hello, my name is Jacek Karolczak. I'm a student of third year of Artificial Intelligence at the Poznań University of Technology. I am also a member of group of horribly optimistic statisticians. I'm glad that you decided to listen to my presentation, during which I will talk about ligand classification, particularly classification using convolutional neural networks. This presentation is based on the work done together with my colleagues within the past 5 months under the supervision of PhD Dariusz Brzeziński. I'm aware that most of the listeners of the presentation are not chemists, therefore the proper part of my presentation will begin with a short introduction to the world of ligands. I will motivate why proper classification is important and how it has been done in the past. Later on, a new approach proposed by my group will be presented, and I will elaborate on translog 3D. I believe that still there is a lot to do, so before answering your questions, I will talk about limitations and possibilities of further improvements. Structure-guided drug design aims to create novel drugs based on potential molecular interaction with proteins in our bodies. This approach to drug design requires structural biology experiments that determine small molecules that bind to proteins. After binding, the protein shape or activity may change, halting disease progression or revealing therapeutic function. One example of a drug developed with this method is an eye drop used to treat high pressure in the eye, which is known as TRAS-opt. During structure-guided drug design, an important step is to properly label binding molecules. The small molecules that bind to proteins are called ligands. Ligands can be either single atoms or groups of a few or even dozens of atoms. The difference in sizes can be easily observed on ligands presented on the slide. The left image shows phosphate, consisting of only 4 non-hydrogen atoms. The picture on the right shows heme, the precursor of hemoglobin, which consists of 75 non-hydrogen atoms. There is, however, also a difference that cannot be seen in the pictures. Balls on images visualize atoms. Balls are of the same size, but this doesn't hold for atoms. The weight of atoms varies. For instance, on the picture on the left-hand side, the central ball denotes phosphorus, that is almost twice as heavy as oxygen denoted by outside balls. The labeling is performed on data obtained from X-ray crystallography, a method for estimating crystal structures through X-ray beam diffraction. The results of the process may be represented using 3D electron density maps, in the case of this particular project, NumPy arrays. In case you remember molecules from the previous slide, you can compare them with the new ones on the current slide. Recognizing molecules can be tricky due to rotation and orientation differences. Image resolution and limitations can also complicate the process. It is not so easy to distinguish atoms inside a molecule or even determine where a new atom starts. Thus, the process of labeling is very hard. It requires expertise, precision, and is time-consuming. Our dataset is based on a subset of ligands found in the Protein Data Bank, an online database in which you can find thousands of protein structures with small molecules. This led to almost 700,000 ligands, being distributed across over 200 unbalanced classes. After an experiment, structural biologists label molecules in electron density maps. This process requires expertise, is time-consuming, and is also prone to human error. That is why there have been attempts to aid structural biologists with automatic ligand labeling approaches. Such approaches are also useful in high-through output screening, where hundreds of drugs are tested and human labor has to be limited to a minimum. Several methods based on core detection and iterative elements addition have been proposed between 2002 and 2007. The accuracy of that method is roughly 48%. However, they are extremely slow. 6 papers based on shape descriptors computation or bounding box detection were published between 2009 and 2014. Despite significantly speeding up the labeling process, they are not very accurate. On about 100 classes, these approaches achieved accuracy levels of about 32%. A new approach named Check My Blob was proposed in 2019 by scientists from Poznań and Virginia. In the classification pipeline, 60 numerical features are computed to describe the ligand at the beginning. There are a variety of features such as mean voxel density and the ratio of second and first eigenvalues. Later on, machine learning algorithms, exactly k-nearest neighbors, random forest, and gradient boosted trees were used to classify ligand based on the computed features. All algorithms proved superiority in comparison to previous methods in terms of time and accuracy, achieving over 67% accuracy. It is important to mention that even though numerical attributes are computed automatically, they were proposed by humans. This means that there is a strong cognitive bias that may limit the effectiveness of the methods. Knowing the limitations of methods enumerated on the previous slide, and knowing that neural networks proved to work well in classification tasks, we decided to test new deep learning approaches. After examining the data, we did some research and decided to use Minkowski engine, a Python auto-differentiation library based on PyTorch. It is dedicated to spatially sparse data and implements all necessary layers such as convolutions, poolings, broadcasting operations for sparse tensors. When the data is sparse enough, using sparse convolution has many advantages in comparison to dense one. Computation is faster and less memory consuming. Additionally, sparse convolution addresses the submanifold dilation problem. The data doesn't get less sparse after applying convolutions. Talking a little bit oversimplifying, but illustratively, the information doesn't fade to voxels filled with zeros. After consulting the problem, a lecturer from our uni, Poznań University of Technology, Michał Nowicki, suggested using Translog 3D. It occurred that the model works well on our dataset, even though it has been developed to solve the problem of place recognition. It's quite surprising that the model works so good for two such different problems. Before proceeding to a detailed model description and results, let's check whether these problems really are so different. The source of the data differs between problems. However, both LiDAR and X-ray crystallography use beams, consecutively laser and X-ray beams. In the details, the result of these processes are different, but for the sake of simplicity, we can make a simplification that both processes produce kind of maps that can be, and actually are, represented using NumPy arrays. In both cases, detected objects vary in size. I hope that you have the intuition for ligands, so I will only talk about place recognition. In the scan, there might be a building and an electricity pylon or a person. Place recognition is applied in robotics, hence the model should be orientation invariant, as objects can be observed from different perspectives and hence have a different orientation with respect to the LiDAR scanner, where z-axis is fixed. Orientation invariance also holds for ligand classification, because ligands can be scanned in different orientations, but ligand classification model should also be rotation invariant. In other words, the invariance should be observed for 3 dimensions. However, hence problems that at first glance look differently are really similar, and it's reasonable to use Translog 3D for the sake of ligands classification. Now, in the following slides, I will iteratively present subsequent modules from which Translog 3D consists of. Please notice that the discussed module will be always highlighted with a color. Before discussing actual Translog modules, I would like to make a caveat. I mentioned that there are significant differences between the size of ligands. The smallest ligands are described with a little bit more than 100 voxels, while the greatest are represented with almost 130,000 voxels. This may cause many problems related to batch size. It's quite difficult to choose a proper size when the instance size varies. It requires a trade-off between supporting all instances and average processor utilization. Thus, we decided to limit the number of voxels in each input. If an input blob representing ligand consists of no more than 2000 voxels, then it's passed without changes. Else 2000 voxels are chosen from the original input. Voxels are chosen randomly. Hence, it was possible to find a reasonable batch size that works on a GPU without running out of a memory. Because of the reduced amount of the data, this operation also speeds up the computations. The very first module of Translog 3D is the 3D sparse convolution module. It's inspired by successes of previous similar architectures like Minklog 3D. It's a shallow convolutional neural network creating new features based on the neighborhood. It consists of only 2 convolutional layers. The first convolution has a 2x2x2 kernel with stride 1. The second convolution has a 5x5x5 kernel with stride 2. Both layers are followed by batch normalization and nonlinear activation function, namely ReLU. It's worth mentioning that the sparse version of convolutional neural networks work faster because point neighborhood is determined using hashing algorithms. Adaptive receptive field module is inspired by selective kernel networks proposed in 2019. As Translog 3D authors claims, its goal is to aggregate information about neighborhood of different sizes. The input data is passed through 5 parallel branches of different receptive fields, from 1x1x1 to 9x9x9. For computing efficiency, branches with receptive fields greater than 5 are implemented by stacking multiple convolutions with kernel size 3x3x3 and 5x5x5. All convolutions but the last one in the branch are followed by batch normalization and ReLU. Then to each branch, efficient channel attention is applied to capture clean and complete structure information. Efficient channel attention was proposed in 2020 and is claimed to improve performance in comparison to the vanilla attention mechanism. Later on, outputs of ECAs is aggregated with a sum of and nonlinearity. Afterwards, softmax is applied to obtain the weighting vector. This vector is used in a gating mechanism as a gating activation vector for the ECA's outputs. External transformer is a module that exploits global dependencies using 6 serial self-attention layers. In order to improve efficiency yet, another attention version is used, namely external attention. It uses external learnable memory units as keys and values. Thus, the number of parameters is significantly reduced. It also allows controlling space complexity, as it is possible to manipulate the sizes of keys and values. If you want to know more about external attention, please see the reference on the slide. Finally, the output of each external attention layer is concatenated by the feature dimension, followed by a transformation to aggregate information from different levels. The last layer of translog, namely NetVLAT, is a generalized version of the vector of locally aggregated descriptors layer, known under the abbreviation VLAT. NetVLAT's goal is to produce a discriminative global descriptor by aggregating local features. NetVLAT learns K-cluster centers and sums the difference between the local descriptors and the corresponding cluster centers to obtain a permutation invariant descriptor. At the end of the layer, a multi-layer perceptron is used to reduce output fitting size to the requirements. The training process was conducted on an NVIDIA GeForce GTX 3080 GPU and took roughly 27 hours. Cross entropy was used as a criterion. To improve generalization, when weight decay was applied with a value of 1 to the power of minus 4. Because of applying weight decay, Adam W was used as an optimizer to avoid problems that occur while using vanilla Adam with weight decay. The optimizer step was set to 1 over 1000. The training set was composed of almost 500,000 examples. A single batch consisted of 64 ligands. We applied gradient accumulation, and hence the optimizer was updating the model weights after every 4 mini batches. I want also to remind you that we used the Minkowski engine framework that is built on PyTorch as a metadata store. For experiment tracking, we used Neptune. Usually, models for Ligands classifications are evaluated not only in terms of top 1 accuracy, but also top 5 or even top 10 accuracy. In all this 3 metric, Translog 3D proved to be able to outperform the current state-of-the-art model, namely CheckMyBlob. We have observed that the results vary greatly depending on the random seed used when sampling voxels. Therefore, the sampling approach still has to be improved to offer stable performance. There are also other cons of the current solution. It lacks interpretability. The last module, NetVLAT, was proposed to create a place descriptor in form of a vector. It is similar to bag of words used in natural language processing. There is only one linear layer following this module, and hence results are in form of a ranking, but not a ranking in which values can be interpreted as probability. In addition, there is a limitation that considers the approach and previous techniques. The proposed approach is a classification one. In the drug design problem, new molecules can be produced. In such a case, the proposed approach is useless because the classification will never predict an unseen class. The results are quite promising, and we hope we will be able to publish them soon, but before, there are a few issues to work out. We want to improve results reproducibility by standardizing the process of limiting the number of voxels in an instance instead of drawing them. We are still looking for a solution that will be computationally efficient. The general idea follows looking for a characteristic points, for instance, taking centroids of clusters. We also would like to improve the interpretability of the results, probably by adding a softmax layer preceded by some linearity. Later on, probably we will use CAPTUM or saliency maps to make the model truly interpretable. Even though we have tested a few models like Minkowski PointNet earlier, we also would like to test a few more models. Translog 3D authors claims that PointNetBlood works in the place recognition problem because of some limitations related to local descriptors. However, this problem seems to be not a problem in the case of ligand classification. We also will check MinkLog 3D v2. The model was proposed in February, just a few days before today, the day I'm recording this video. Authors of MinkLog 3D v2 claim that the model works better than Translog 3D, so we definitely want to check its performance in the problem of ligand classification. Before I finish, I would like to remind you, for the past 20 or 25 minutes, I have been talking about ligand classification. Ligands are small molecules, very often potential drugs, that bind to proteins. All previous approaches were not based on neural networks. We proposed a new approach that uses the current state-of-the-art place recognition models. The results are superior to existing approaches, but also have some limitations, and overcoming these limitations is our current main goal. I would like to thank my colleagues, particularly Ania Przybylowska, Witek Teisner, Konrad Szewczyk, and Wojtek Tomczak, for the cooperation from which results are presented today. I want also to acknowledge the huge impact of PhD Michał Nowicki for insight into the place recognition problem and shared with us a GPU for experiment. At the very end, last but definitely not least, I want to express my sincere thanks to PhD Dariusz Brzeziński, who supervised the project but also was an important support for me while preparing this presentation. Thank you for all your knowledge, advice, kind words, and time. This is the end of the presentation. Thank you for your attention. I'm looking forward to answering your questions.
Awesome, Jacek. We're going to have Jacek joining us here for the live Q&A, of course. Hello.
Hello, hi.
Awesome to see you. I'm not going to lie, I study with Jacek, so great to see you.
Great to see you too.
Right. We've got 4 questions here on the chat. Let me start with the first one from Alex. Which sources, like blogs or books, would you recommend for exploration of that topic?
So it's kind of a complex question because I don't know what you mean by the topic. If you mean the ligand classification, it might be a little bit difficult. At least for me, it was to understand what's going on because most blogs are written so by experts, they are kind of difficult to understand. So probably I would suggest to you reading paper written, the introduction to papers written by Dariusz Brzeziński, whose name was mentioned many times today, but it's reasonable to do it one more time. And if you are interested in place recognition, probably you are studying at best university, at least in our country, because there are many experts who are actively working on it. And if you are interested particularly in these methods based on Minkowski engine, probably you can look for GitHub named Yac99. This is a professor from Warsaw University of Technology who is probably the most active person right now in this topic. I unfortunately don't know any books or blogs because both are so narrow for at least for now.
Yeah, sure. Okay, we've got most upvoted question now from Martin. What was the hardest thing in your project?
Okay, probably the size of the data and the fact that there are over 200 classes and they are imbalanced. So yeah, I think it's the biggest problem. It's difficult to understand what you really want to obtain, and when the data is unbalanced, it's even harder.
Okay. Yes, I think we can go to the next question. I think I've got maybe internet issues, or you may have internet issues. Not sure about
Okay,
that.
so
But
could you confirm that you
let's
hear
maybe
me?
come. Yes, I can. I can hear you. Not sure on what
Okay.
side was the internet issue, but yeah.
Okay.
Highly likely it was on my side, yeah. But the next question, actually from my side, I will merge two of my questions. Have you considered other architectures than Translog, or was that something that came up naturally? You mentioned that it was proposed by Michał Nowicki, but maybe you could elaborate a little bit on that. And were you forced or to change or adapt some parameters of the building blocks of Translog, which you talked about extensively?
Okay. So we also have tried to use another, maybe even more than one, approaches like Mink PointNet or Mink Log, but they performed worse. And this is interesting that the mentioned researcher Michał Nowicki told us that probably Translog will be best for this problem. And we also a little bit modified the architecture to meet our requirements, for instance, the size of the output.
Mm-hmm. Awesome. I think that concludes. Jacek, thanks once again for your contribution to Ghost Day. Awesome to see you, and yeah, thank you.
Thank you. Bye-bye.
Bye-bye.